everyone. This is Unit 3, Section 1, Ionic Bonding and Properties. So this unit is mostly going to be about ionic bonding. At this point, you already should feel comfortable writing formulas, and you should already feel comfortable with understanding that this bond is between ions, and we have a positive thing attracted to a negative thing. So when you're going through these notes, I want you to be writing down the notes, writing down your information, and then write questions off to the side for anything that you don't understand. That way we can cover it more in depth in class. So far we already know that in this picture all the way on the left we have a sodium ion. And we know that this sodium, or we have a sodium atom, and we know that the sodium atom has our 1 valence electron here. And we know that when sodium becomes an ion, we know it becomes a +1 charge. So we have to think about where that electron is going to go. It's going to go off into the wilderness. So far, that's as far as we've learned. But then I've got a chlorine atom. And we know that chlorine has 7 valence electrons. So sodium had 1, chlorine has 7. Sodium gets rid of its 1, and chlorine, in order to become a Cl-, needs to gain an electron. So where's that electron going to come from? It's going to come from sodium here. So now, rather than just accepting that atoms will gain or lose electrons to form ions, now we're going to transfer that into where are these electrons coming from? Well, they're coming from other atoms. And the whole purpose is that they're trying to achieve a stable octet, and they're helping each other out, where one atom is giving its electron to another atom in order for both of them to be happy. Then, because we have our positive charge and our negative charge, that's what causes the ionic bond, because we've got a positive thing attracted to a negative thing. So your key word here is transferring. An ionic bond is a bond that forms by transferring electrons from one atom to another. So in a test question, I will be looking for that term, transfer. I expect to see that when you're talking about ionic bonds. This changes their charges, making them ions. Remember, it's ionic. The way we form an ion is by gaining and losing electrons, and the whole point of an ionic bond is that it's a bond between ions. Your positive cation generally comes from your metal, and your negative anion always comes from your nonmetal. So, if I'm asking you what types of elements form an ionic bond, you are going to be telling me that it is a metal plus a nonmetal. So this is what we talked about on the last slide. When sodium gives up its electron, it's going to give it to chlorine. Remember, this also goes back to electronegativity. Chlorine is really electronegative. It really wants an electron. So it's got a high nuclear charge. It's going to pull that electron in that sodium gave up, and it's going to form the chloride, Cl-, and sodium has the Na+. Now those two things are going to be attracted to each other, forming that compound. Remember that positive and negative ions attract, forming a compound. So here's kind of what this looks like. So I'm going to move this up a little bit. If I have a positive thing, this is Na+, I'm trying to write this with my fingers and it's not going great, I forgot my pen, and then Cl-, we've got sodium and chlorine, but when I get a bunch of sodiums and a bunch of chlorines together, they're going to go around, so we've got another sodium, I've got another sodium, and I've got all my sodiums surrounding the negative chlorine, and I'm going to surround that with some more chlorines. Chlorine, chlorine, chlorine. Okay, and this is because anytime we've got a positive thing, it's going to be attracted to the negative thing. So this sodium is attracted to that chlorine. This sodium is also attracted to that chlorine. This chlorine's attracted to that sodium. It's also attracted to that sodium. These two are attracted to each other. These two are attracted to each other. These two are attracted to each other. These two, these two, these two. Boom, boom, boom. So you can see that when we talk about ionic compounds coming together and we have a lot of ionic compounds together, we end up with this structure where we've got positives and negatives next to each other, and it ends up forming what we call a crystal lattice structure. So this guy is our crystal lattice structure, and it's really, 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 really strong. Because think about it, look at all of that attraction that I drew with those little attraction lines. Each one of those is a form of attraction. That's a ton of attraction. It's going to make this structure really, really, really strong. Everything else we're going to learn about ionic properties is based off of this idea. If you understand why an ionic compound forms a crystal lattice, and if you truly understand what's going on with the crystal lattice, everything else just kind of makes logical sense. So, because that's such a strong crystal lattice, on the right, all the way on the right this is what that crystal lattice looks like in 3D. This is what that looks like in real life. Because of that crystal lattice, because there's so much strong attraction, it's going to be solid at room temperature. Because remember, if particles are close together, they're going to be a solid. And these guys are really close together because they're really attracted to each other. And again, that's because of the positive and negative. Now let's think about that attraction. Okay, I'm going to first kind of skip down and we're going to talk about why crystal lattices or why ionic compounds are not malleable. So they're not malleable. That means that they are brittle. They are easily broken. And really, if you look at this picture, this is exactly what you need. So if I take a crystal lattice, remember this is our crystal lattice structure, and it's really attracted right now because we've got the positives attracted to the negatives. But if I hit it, like this hammer is doing, then what's going to happen is it's going to shift the crystal lattice structure. And see how we've got two positives next to each other, and I've got two negatives next to each other, and two positives next to each other? Remember, like charges repel. They don't want to do that. So what's going to happen is a crack. It's going to break. So brittle means that it can be easily shattered or easily broken. And it's really just because when that crystal lattice structure gets misaligned, it causes repulsion between the like charges. Now here's some of the other properties. Ionic compounds conduct electricity when they are dissolved in water that's aqueous, but they aren't conductive when they are solids. Now we're going to talk about why in just a hot second. Most of them, or many, are soluble in water. Soluble means able to dissolve. So many are soluble in water, and water is a polar molecule. You guys should remember from bio, hopefully, that water is polar. And that means that water has, that's not a pen. That means that water, if I look at the molecule of water, you guys have seen this before, it looks like this. This side of water is really negative, and this side of water is really positive. We'll get into why water is polar next unit, but look, it's got a positive side and a negative side. So on the next slide, I'm going to talk about why things are able to dissolve in water, why the ionic compounds are able to dissolve in water, and then that will lead us into why they are conductive when they are aqueous but not as solids. They also have a very high melting point. So when you melt something, you pull this formula unit away from the next formula unit. You're separating the compounds. You're separating one formula unit from another. When we're talking about ionic compounds, we refer to them as formula units. So each one of these positive and negative things is considered to be a formula unit. It's essentially the same thing as if I was referring to a molecule of water. That is a different type of bond. For ionic bonds, we talk about them in reference to formula units. So when you boil something, you're separating the compounds. You're separating each of the formula units. And if they're really attracted to each other, it's going to take a ton of energy in order to separate them. So because of how strong the crystal lattice structure is, it leads to a very high melting point and boiling point. So it also causes it to be brittle, like we talked about at the beginning of the slide. So now let's get into why ionic compounds dissolve in water. So there's a fantastic video. It looks like this. that I linked onto my website. I want you guys to go pause this and go watch that other video. So hopefully what you saw was the polar water. Remember, we've got a positive side and a negative side to water. And remember, in our crystal lattice structure, we've got a positive and a negative. So what happens is the positive side of water here is going to be attracted to the negative chlorine. And it's going to surround the negative chlorine and it's going to pull it out of the crystal lattice structure. This is what happens when a compound dissolves, or an ionic compound dissolves. It breaks up the crystal lattice structure, and we say that it dissociates. I'm going to write that word. Dissociates in water. So that means that it actually separates into its ions. We call that dissociation. So then we get all of the positive side of water attracted to the negative thing, and we get all of the negative sides of water attracted to the positive thing, and it pulls it out of that crystal lattice structure. That's what happens when it dissolves. And the reason why ionic compounds are able to dissolve in water is solely because there's a positive side to water and a negative side to water. And remember, opposites attract. So the negative side will be attracted to the positive side attract to the negative, and so on. So we talked about why they are soluble in water, but we still haven't really talked about why they are conductive when they are liquids or when they are solids. So in order to explain that, you really need to understand why electricity occurs, or why conductivity happens. So electricity conducts because of free-flowing electrons. So that means that we are having electrons that can move. They can move from one atom to the next, or they can move within a bond. They're not held really, really tight. Now, if we learn anything about an ionic bond, it's that it's really strong, and it's that it's really rigid. So, if electrons aren't able to move, they can't conduct electricity. We call those insulators. Now, the reason why ionic compounds do not conduct as solids is because the electrons are held really, really solidly in that crystal lattice structure. It's really rigid. The electrons can't move, they can't flow. But remember, when we conduct electricity, we dissociate into ions. We broke the crystal lattice structure. So now the electrons can move from one ion to the next, and it allows us to conduct electricity. When ionic compounds melt, when they become liquids, they dissociate into ions, and that also allows them to conduct electricity. So ionic compounds conduct electricity when they're liquid or aqueous, but not as solids because of that crystal lattice structure keeping us from having free-flowing electrons. So here's just a really good visual of that. So here we have just straight up water, H2O. Now H2O is a type of covalent bond, which we'll get into next unit. But H2O doesn't conduct electricity if it's just pure water. But Miss Nyman, my parents tell me not to go into a swimming pool when it's lightning because it will lightning me. What is a verb for that? Struck by lightning? There we go. We'll get struck by lightning. Now the reason why that happens, if you were sitting in just a pure water pool, you'd be totally fine. But the problem is that, one, you have ions all over your body. Y'all are sweating all the time. That is ions just going into the water. And then we also put like chlorine and other ions into our water. And remember, I said once we get ions dissociated into the water, it can conduct electricity. So we can see that our light is not on for pure water, but it is on if we have ions in it. The other thing I want you to see is that over here with our ionic compound as a solid, we do not have our light on, meaning it's not going to conduct electricity. So let's get into a little bit about metallic bonds. So I know that this unit is primarily about ionic bonds, but this just fits really well in here because we just talked about electricity, we just talked about why ionic compounds can conduct electricity, and the metallic bonding is not a huge significant portion of what we're going to talk about this year. So I'm just going to toss it in right now, and there's just not a massive amount of information that you need to know. So what you need to know about a metallic bond is, remember that's our third type of bond. Our second type of bond is the next unit. What we have is we get this thing called a C of electrons or delocalized electrons. So it happens when metals get together. Let's say that in this picture, these are all copper atoms, sure. So remember, copper can kick out electrons and it can become positive. So we've got our copper cations, and then we just have these electrons that are just kind of chilling, hanging out. They're going to whoever. They just can free flow. They're not assigned to any particular atom. It's just a sea. There's just electrons hanging out in between all the atoms that anybody can use freely whenever they want. So this is not a rigid structure. This is a really kind of loose structure. So because we've got these delocalized electrons, they can move freely. So these delocalized electrons can move freely, which is the reason why metals are conductive as solids. Because when they are solids, they have electrons that can move around wherever they want. Oh, look how cute the metallic bond is. Look, they're all sharing. That's adorable. So again, free-flowing electrons cause the electrons to be moving, and therefore we can conduct heat and electricity as a solid for metallics. We can also conduct as a liquid or an aqueous. We can conduct it whenever, because metallic bonds always have those free-flowing electrons. This is also the reason why metals are malleable. If metals are malleable, or if metals have these free-flowing electrons, then when they're hit with a hammer, they're going to deform, but they're just like chilling loosey-goosey. It'll change the shape and it's not going to break because it's not a rigid bond. This also allows it to be ductile for the same reason. Now we're going to get into melting point and boiling point and the hardness and all that stuff, and that really has to do with how strong the cation is, the nuclear charge, and all that stuff. We're not going to get too far into that really at all. But the melting point, the boiling point, the hardness, the bond strength itself within a metallic bond can be very, very different. A sodium metallic bond is very different from a copper one or from a lead one in terms of how strong they are. And we're not going to get into the trend so much with that. But again, see how close in the structure, how close the atoms are together? That causes it to be a solid at room temperature, except for mercury, which is a liquid. So at this point, what you should be recognizing is how important the structure is to the properties. And I want you to remember that just because we have individual atoms, and we know that the individual atoms have their own specific properties, that doesn't necessarily mean that they'll have the same properties when they are in a bond. So remember that if I'm talking just about, let me move up, and we're going to go back a little bit. If I'm talking just about copper, we know that copper itself is malleable, it's ductile, it's solid, and we know that because of the metallic bonds. That's why copper has all of those properties. But if I get copper with chlorine and they're bonded together, then it's going to have different properties. And that's because of that chemical bond. So copper chloride is actually green. It's a green solid. It's crystally, and that's because it's an ionic. So ionic compounds do conduct electricity when they're aqueous and when they're liquid, but it's not because they have a metal. It's because of the crystal lattice structure. So properties are based off of the structure of the compound, and it's really, really important that you understand what the structure is, and then you can relate what you know about the structure to the properties of the elements themselves or of the compounds themselves.